do Friday, March.
Okay. All right, so we're going to do a little tougher one today. We did a polynomial function the other day. I think it was x cubed minus, I don't know, 6x squared or something like that. Anyway, we're going to try a little tougher one here. We're going to analyze it, go through all the different properties of it, and then draw a rough sketch. Okay. First thing, kind of off our checklist here, is the domain. All right. Domain of this function, what would it be? What do you need to think when you think about domain?
You put the 0 for y. What is going to make it not have an x value?
Yeah, I try to think about what x values don't work versus what x values do work. Okay, and by working, I mean you can actually plug in that x value and you'll get an answer for y. So find the ones that you can plug in and can't get an answer for y.
2. Right.
2?
Negative.
Negative 2. Okay.
There are no square roots.
X. So therefore, if you would plug in a 2 for x or a negative 2 for x, you would get undefined. So therefore, negative 2 and 2 are not in the domain. So if you wanted to write the domain out, you'd write negative infinity to negative 2, and then negative 2 to positive 2, and then positive 2 to infinity. Okay. The other notation that you'd see is all x values where x does not equal 2 and x does not equal negative 2. Okay? So that would be just different notation you might see for that. We use interval notation. I think that's just easiest to understand, so we kind of stick with it. Okay? So there's your domain. So you kind of already know there's going to possibly be some asymptotes or holes potentially in this graph. I mean, we haven't really gotten there yet. But you kind of already know that because there are a couple x values that are not in the domain. Okay? X-intercepts. How do you find x-intercepts?
Make y equals 0.
Make y equal to 0, solve for x. Okay? So, x-intercepts,
Do not exist.
if you make y equal to 0, and then set that equal,
You just
in order for a fraction to equal 0, the numerator would have to equal 0. So in other words, x squared plus 1 would have to equal 0. Subtract 1 square root, you get the square root of negative 1. That is not a real number, so therefore there are no x-intercepts. So this graph will not cross the x-axis anyway. Okay. All right. Y-intercepts. Okay, Y-intercepts, how do you find those? Plug in 0 for x. So y equals 0 plus 1 over 0 minus 4. So negative 1/4. So 0 comma negative 1/4 is your y-intercept. So if you were kind of in the process of drawing a graph, put the first point at least on your graph. That's the first point we found. Okay. Vertical asymptotes. Where do vertical asymptotes occur? What I kind of marked down is what do you look for? Whatever makes only the denominator equal to 0. So will that be our 2 and negative 2 in this case? Do they just make the denominator equal 0? Okay? So, vertical asymptotes would be x equals 2 and x equals negative 2. So, you could add a little bit more to your graph then at this point, if you're kind of graphing it as you go. Okay. Let's see. Horizontal asymptotes. How do you find horizontal asymptotes?
Find
Limits as
Limit
it approaches
as-
negative infinity to
Yeah.
positive infinity.
As we go way to the right, way to the left, okay? The limits of the function as x goes to positive infinity, the limit as x goes to negative infinity. Okay? So horizontal asymptotes, we want to find the limit as x goes to infinity of x squared plus 1 over x squared minus 4. For some of you that see it, logically, you'll get your answer. For some of you that remember the trick, we divide everything by the highest power of x in the denominator. And then you essentially plug in infinity, but what will the horizontal asymptote be here as x gets very, very large? 1, yep. Because really you have x squared over x squared. The plus 1, the minus 4 have such a little impact on the value that you're going to get really, really close to 1. What we had you guys do to show this, we had you divide everything by the highest power of x in the denominator, so I'm going to divide everything by x squared. So I get the limit as x approaches infinity. X squared over x squared would be 1, plus 1 over x squared over 1 minus 4 over x squared. And then by substituting in a very large number for x, what's 1 divided by a very large number essentially equal?
0.
0. So you have 1 plus 0 on the top, 1 minus 0 on the bottom. You get 1 over 1, which is 1.
And same for-
Would it change anything for negative infinity?
Nope.
Nope, negative infinity, because you're squaring it, you end up getting a positive on positive. Okay, so that tells me at the ends, we have a horizontal asymptote, y equals 1.
Even if it weren't squaring it, wouldn't it be basically a giant negative number on the bottom, so it would be essentially negative 0? Like, if it weren't squared, wouldn't it have essentially still been
Yes.
essentially negative? Okay.
Yes. Yeah, I guess I wasn't looking here, I was looking at this one. But yes. Yep. Okay, so we do have a horizontal asymptote at y equals 1. I'm not going to draw that yet because I don't want to draw it across the entire graph because it might cross it in the middle. Although I highly doubt it since the graph never crosses the x-axis. I'm guessing it all stays down there potentially. Okay. I probably could draw my my horizontal asymptotes now if I wanted to, but I'll hold off on that for a second. Okay? Alright, intervals of increasing and decreasing. Alright, what do we gotta do? Quotient rule, yep, quotient rule. So, what are we gonna have? Who's got it?
Low,
Okay?
x squared minus 4.
Alright, steel trap, here we
D
go.
high, which would be 2x, minus I, which would be x squared plus 1,
Sounds great.
times D low, which would be 2x, all over the square of what's below,
X squared minus 4
which would
squared.
be x squared minus 4 squared.
Beautiful.
Thank you.
You should be the voice for an audiobook. That was just so wonderful.
Blissful.
What is this again that we're?
We're finding the increasing and decreasing intervals. In order to do that, we need to do the first derivative, find our critical points, and then test. This right here is 2x cubed minus 8x. This right here would be 2x cubed plus 2x. And I'm taking this quantity and I'm subtracting that quantity, and what do you get?
Negative 10?
Negative 10x.
Oh, yeah, minus.
You got negative 8x and you're subtracting another 2x. And the 2x cubes cancel each other out, so you're just left with a negative 10x in your numerator. Speak up if you don't see it. I did show every step there. All right, so to find our critical points, we need to ask ourselves, when is the first derivative what? Equal to 0 or undefined? I think we can start to see this. When would this first derivative equal 0? If x was 0. Okay, if x was 0. So, critical point, x equals 0. How about, when is it undefined?
2 and -2.
2 and -2. Okay? If I plug in a 2 here, 2 squared is 4, 4 minus 4 is 0, 0 squared is 0, can't have 0 in the denominator.
Wait, why is 0 critical point?
Negative 10 times 0 is 0, and therefore the derivative would equal 0. Because we have to ask ourselves, when is the derivative equal to 0? Because our derivative is a fraction, when is a fraction equal to 0? When the top is 0, right? And the only way for the top to equal 0 is if x itself was 0. Okay? So when x equals 0, x equals 2, and x equals -2. Right? So on our number line here, those are our critical points. Let's test other x values that are between and on the outsides of those critical points. Test them by plugging them in to the first derivative to see whether the function is increasing or decreasing on that given interval. Okay? So we'll try -5. I plug in -5, I'll get a positive number on top. I'm squaring anything down here, so that's also going to give me a positive number on the bottom. Positive divided by positive. Positive.
Big positive.
Okay.
That's me. Someone call.
I check -1.
Okay.
-10 times -1, that's a positive number. If I plug in a -1 here, I'm still going to get another positive because anything squared is going to be positive. So again, it'll be increasing. If I try a +1, I'll get a negative value on top with a positive value on bottom. Negative divided by positive will be a negative. And if I have to. And if I try a value that's greater than 2,
But like,
alright, take 5 for instance again. -10 times 5, that's give you a negative value on top with a positive. Negative by positive, you'll be negative right here. Okay?
Could you at least just have 4 on the leftmost,
Oh, no.
so then it's just
Oh,
4,
no.
3, 2, 1? Please? Just show a bit of mercy.
Nope.
Just
Alright.
Just a smidge.
Azan's a savage.
So, now we have its increasing and decreasing intervals that we could write. It's going to be increasing from -infinity to -2. It's going to be increasing again from -2 to 0, then decreasing and then decreasing. Alright? We'll write those. So increasing -infinity to -2, and then -2 to 0. Decreasing 0 to 2, and then 2 to infinity. Do you have any relative extrema then? Local mins, local maxes?
At 0, 0.
At 0, right?
Or,
Okay.
sorry, 0, negative
Cause that's where it switches,
0.25.
wherever it switches from positives, increasing to decreasing. You know you'll have a relative maximum right there. And we've actually already found that coordinate because if x is 0, okay, we already know that y is 1/4. So I know this is going to be a local
Well,
maximum.
negative 1/4.
Okay, so I have a local max at 0, negative 1/4.
Does it matter that it's local?
Okay.
Like absolute?
Not going to be absolute because we don't have
Because
a
it goes to
closed
infinity and negative
interval.
infinity.
Do I need to write local?
Yes, local or relative.
Got it.
Yep, local or relative. Local or relative is just, only time you can say absolute is, on a closed interval.
At the end.
Mm-hmm, yep, so I would just say, call it a local or relative all the time. Okay.
What's the sitch?
Alright? Okay,
Impossible.
You're just impossible.
you probably could draw, hey, listen,
Sorry.
you probably could draw the part between the two asymptotes right now,
Mm-hmm.
don't you think?
Yeah.
Mm-hmm.
From -2 to 0, it's increasing. From 0 to 2, it's decreasing. So if you had to take a kind of a guess, what do you think?
Parabola.
Kind of an upside down parabola, if you had to guess?
Maybe slightly fatter, but yeah.
Okay. I mean, it's not going to have any extra waves in there. Okay. So this could be kind of a rough,
Very
rough sketch there.
Beautiful.
Okay. All right. So we've done our increasing, decreasing intervals. We've done our relative extrema. We need to do inflection points and concavity intervals. Yeah.
Yeah.
So this is like combining everything we have done.
Yep.
Take out the whole
That-
freaking
Yikes.
for one problem.
Is
That's
this
the
our
part that I'm
semester
kind of a
trials?
little.
We all would.
Will we have to be dividing polynomials? So won't this turn into dividing polynomials?
Excuse me.
Won't this eventually make it so that we have to divide polynomials? Or did I do it wrong?
No.
No.
Okay, no, I don't think so. So, now we gotta do second derivative.
So that's low. D high.
I would possibly debate foiling the denominator first, so then I don't have to use a chain rule. You see what I'm saying there?
Yeah. I mean, I
Don't have to.
Nah. I'm
Okay.
insulted.
Some of you wanna attempt it, did you already attempt it the way it is written?
I think so, but I
Okay.
think essentially I did do that, it's just not
This.
picking out the steps.
X squared minus 4 times itself. X to the 4th. Minus 4x squared minus 4x squared, so minus 8x squared plus 16.
That was quick.
Foil. Yeah, I don't know if that's,
Is that really any much better?
I don't know if it's gonna be any better or not.
That's a lot.
Yeah, it is better for what I had.
I'm gonna go with it, just see how it looks.
Because I remember doing the training for it and
So, low. D high. Minus high. D low, so 4x to the third minus 16x.
I guess maybe it's not.
All over the square of what's below.
Oh, actually it just took out a single step. Never mind.
Your video's at 20 minutes now, by the way.
So this is the part, cause I mean,
Square the bottom, oh, you did it on that.
cause if we factor that out, never mind.
You square the bottom, right?
Yeah, he's good, Bob.
Thank you.
I'd first probably take out the -10 from both.
Boil it, that's all I gotta say.
Real quick. Negative 10x to the fourth plus 80x squared minus 160. Negative 40x to the fourth plus 160.
You might wanna
X
take out the
squared.
10x, or just the 10, the -10, I mean. 'Cause
Yeah, I see that. I don't know if everybody would have noticed that, but
Oh,
yeah.
Okay. Just so they're not so big of numbers.
Yeah, that would be fine. I just don't know if everybody would have seen that.
Okay.
So, I got negative 50x to the fourth.
Don't you mean 40x to the fourth?
What am I missing?
40x to the fourth, not 50x.
Oh, wait a minute, that actually would be adding
Yeah.
positive 30, right?
Yep. What was that?
Magically appear. Alright, so negative 10x to the fourth minus a negative 40x to the fourth would be a positive 30. 80x squared minus 160x squared, that would be minus 80x squared, and then minus the 160. All over x to the fourth minus 8x squared plus 16 squared.
Oh boy. This is too easy, almost. Almost, I said. Excuse me. Apology accepted.
You already got the back.
Alright, let's see. I could possibly see where maybe this didn't help us with the denominator per se, because I'm actually going to probably go backwards on this now. Because looking at this, you probably don't see what makes the denominator equal 0. But remember, what was this inside the parentheses here?
X minus 2x plus 2
This right here.
squared.
It was x squared minus 4 squared.
So it's still.
So really, I have x squared minus 4 now just to the fourth.
Yeah.
Because this amount was really this right here, and this right here was really this. So I had x squared minus 4 squared, and then I squared it again. So I don't know if that necessarily helped. Does our numerator look better than yours or not?
Yeah, it does.
Okay. That's the
I
only reason.
accidentally missed a x in there also, so that helps.
Yeah, boy, this factoring looks great, if it even is.
Again, you might want to start by taking out 10.
Yeah.
Or negative.
So
yeah, no.
3x to the fourth minus 8x squared minus 16. Then you can check the special factoring trick to see if that's factorable. 3 times negative 16 gives me negative 48. Then I'm looking for things that multiply to negative 48 and add to negative 8. So 148, 224, 316, 4, and 12. So I could get them there.
We got a winner.
So negative 12 and 4. Divide those by A. So negative 4 over 1 and 4 over 3. Put the x's at the bottom. Oh boy.
He keeps saying that.
Yeah.
So
Probably not a good sign.
this is.
So then I have x squared minus 4
X minus 4.
and 3x squared plus 4.
Oh, because they're x squared, okay, that makes sense.
Oh. Should we expect like
Wait,
one
I'm
like this on the
really
test?
Why not? This has been a lot of fun.
Yeah, we allow for the check too.
Yeah.
Wait, I have a.
Yeah.
Why? So you did 4 and 12?
Negative.
Negative 12 and
Why?
4 because they had to add to make negative 8.
Okay.
You should put some sines and cosines in there.
I agree.
Stop
That'd be
talking.
fun.
Include like phase shifts and stuff.
Mhm.
Nice, that's great.
No.
It has nothing to do with this.
That's, hey, it's a take-home test. We need to be able to do this.
This isn't on the take-home test.
He's
gonna put it on.
I thought it's too late.
On there.
This could cancel one of those.
Yeah, seriously, who's composite?
3x squared plus 4, can that ever equal 0?
What?
No,
3x squared plus 4, can that ever equal 0?
No.
Okay.
and it's only the numerator that we care about for this, cause we're equaling 0 as long as it doesn't cancel out in the bottom.
Yes.
So there are no values where the second derivative is equal to 0.
Wait, 3x squared.
Because if you set that equal to 0, you'd subtract 4, divide by 3, you'd be at negative 4/3, then you try to square root negative 4/3, and you'd get an imaginary.
I was thinking plus 4/3.
Yep.
I got a little.
What, baby? This is going to cancel this.
Yeah.
This is going to cancel one of those down there.
And then you just have to worry about the 3x squared.
So,
and the square.
therefore, the second derivative is never equal to 0. It's undefined at 2 and negative 2 again. So actually, you can do your second derivative test with simply 2 and negative 2. Running out of room here, but I don't want to have to
So
rewrite.
we did all of that to come back with
Right?
numbers we already had.
And then if you check to the left of negative 2, so like negative 5, positive, positive. I check negative 5, that'd be 25 minus 4, 21. Positive,
Positive.
okay? So tells me it's concave up over here.
And then positive again.
Check in the middle, so like
Oh.
0. So positive, positive.
Negative. Or
Negative. So it tells me it's concave down in between, which we kind of knew that already. And then to the right of 2, so like positive 5, positive, positive, positive. Okay? So it's concave up again to the right.
This is great.
Will we at least have the steps on our test?
So,
Like the
what
8
steps?
steps saying find this and this.
I'll tell you what to find, yeah. Yep.
So we won't just be like, you need to find the things that we usually find.
So now if you recall, we had a horizontal asymptote here at 1. We know it's concave down between them, and it's concave up on the outsides. Remember, it approached 1,
It's concave.
and it was also,
concave.
it was increasing from negative infinity to negative 2, right?
Yeah.
So it makes sense that the graph probably looks something like this
It's
here.
also concave up.
It's increasing and concave up. It was increasing from negative infinity to negative 2. Tell me yes, I don't remember
Yes.
from my, okay? How about from 2 to positive infinity? Was it increasing or decreasing?
Decreasing.
Decreasing and concave up though?
Yes.
So it would make sense that the graph would look like this.
Yes.
Okay.
Which if you look at it and you calculate it.
And
it's
voila.
Easy.
What a wonderful problem.
So
Yes, let's do another one.
Yeah.
if